Hey guys, so with this video, we're going to talk about isotopes and how to calculate the average atomic mass. So as a refresher, if you're looking at the periodic table, and for example, you look at carbon, you have the atomic number 6, you have the symbol C, you have the name, and then at the bottom you have 12.01. And that is the average atomic mass. And the reason why it's an average is because elements come in a variety of isotopes. And remember, isotopes are atoms with the same atomic number, so the same number of protons, but they have different atomic masses. And this is because they have a different number of neutrons. So their mass is protons plus neutrons. So if you change the number of neutrons, you change the atomic mass. And so the average atomic mass is the weighted average of all the isotopes of an element. Now, the reason why we say it is a weighted average is because all isotopes, I'm just struggling with spelling isotopes right here. Let's try that again. Isotopes have different relative abundance. And so that relative abundance is really important. This is basically how common that isotope is in the world. And so if we look at this example in this box here, it says a sample of cesium is 75% cesium-133, 20% cesium-132, and 5% cesium-134. So this means that not all of them are exactly equal. A weighted average is also how your chemistry grade is calculated. So, for example, you know that your test grades are worth more than a quiz grade. Well, same thing here. Cesium-133 has a higher percentage because it's more common. And so this means that the higher the percentage, the closer it will be to that value. And so if we do this practice problem, we can see that what you do is you first write down all of them in their isotope form. So cesium-133, we have cesium-132, and we have cesium-134. And what you do is you multiply the mass number, which remember the number in the top left corner of a symbolic notation is always your mass number, and we multiply it by the percentage, we multiply by the percent abundance, so cesium-132 is 20%, and cesium-134 is 5%. So you multiply by their percentage, so 133 times 75 will give you 9,975, and then 132 times 20 is 2,640, and then 134 times 5 is 670, and you add all three of those together. So we add all their isotopes, and when you add all of them together, you get 1, 3, 2, 8, 5. And what you do is, because all of these were percentages, your very last step is to divide by 100. So when you divide by 100, you get 132.85. AMU, atomic mass units, because that 133, 132, 134, that's all AMU. And so when we look at this answer, we can see that if we were to round that to a whole number, we would get 133, which is also the isotope that had the biggest percentage, which makes sense. The larger the percentage, the closer our answer is going to be to that number. And so, yeah, that's how you calculate average atomic mass. You multiply by their percentage, add them together, and then divide by 100. So let's do a couple examples. So problem A has iodine 127, iodine 126, and iodine 125. So we change the symbolic notation to isotope notation. So I-127, I-126, and then I-125. We multiply by their percentage. So we multiply this one by 80%, by 17%, and by 3%. And so 127 times 80 is equal to 10,160. And then 126 times 17 is 2,142. And then 125 times 3 is equal to 375. We add them all together, and you get 12677. And then the very last step is divide by 100. And when you divide by 100, you get 126.77 AMU as our answer, which makes sense because if you round that to a whole number, you get 127, which is the closest, or the isotope with the highest percentage. And so, again, we can do that for problem C. Problem C is referring to iron 55 and iron 56. So they're only 1 neutron apart, but iron 55 is only 15% abundant, whereas iron 56 is 85% abundant. And so we would expect, because iron has the highest percentage, for it to be the closest. So 55 times 15 is 825, and 56 times 85 is 4,760. And so we add them all together, and we get 5,585. And then our last step is to divide by 100. And when we divide by 100, we get 55.85 AMU, which if we were to round that to a whole number, we would get 56. Much closer to 56 than it is to 55, which makes sense because we have that higher percentage with iron 56. So overall, a pretty easy calculation. Just remember, you always multiply the mass number times the percent abundance or relative abundance, and then you divide by 100 after you've added them all together. And so those are the main steps, and you should continue to practice.